Okay, so symmetry is moving along. So let's just do this. See note number 1. Talk about some rotations and angles real quick and some other definitions. So some of this you've probably seen, just review it, maybe not if you haven't, it's not too complicated. Rotation angles. Rotation angles. Anybody know how many degrees there are all the way around the circle? 360. Right? 360. It's okay. It's your brain's been shut off for months. Yeah. So if I have, say, my XY coordinate plane here, X, and that's Y, okay? And to rotate something at, like, let's say there's a line segment starts at the origin and goes out to here, right? If I want to rotate it in a positive direction, it goes this way. Well, so yeah, but first of all, positive means we're rotating counterclockwise. You know what that means, right? You know where the clock spins. And the negative would be clockwise, okay? So if we start here, we've rotated 0 degrees, right? And then, like you said, that would be 90 degrees to there, positive 90. And then if we keep going to here, how many degrees is that, anybody? 180. And if we go around here, how many is that? 270 degrees. And then all the way back around, we're back to 0, but we made the move, so it's actually how many? That's your 360, okay? And so positive goes counterclockwise when you rotate, okay? It's positive. And that's actually something you'll need when you get into Algebra 2 and trig and calculus. You need to know positive is counterclockwise, okay? Some definitions here. For polygons, you guys know what a polygon is, right? Polygon. It's just some shape with multiple sides, right? Poly meaning many, it's not specific. You know the names of any particular polygons? What shape is the stop sign? Octagon, right? 8 sides. Hexagon, if you turn a bolt, or, you know, usually they're 6-sided, or hex-headed screws, or hex-headed bolts, 6 sides, right? What's the shape of 5 sides? Pentagon, okay? So if you don't, not too familiar with those, you probably should spend some time getting on Google and review your polygon names, okay? Because I got to assume that you know those fairly well, because we'll talk about them. If you know them, it's, you know, that's the thing. You guys sometimes don't wonder. You sit a lot of times and you just, I don't know, no way of finding out. I didn't have what you had when I was a kid. You guys had in your pocket the entire body of knowledge that mankind has generated for the last 10,000 years. And you don't even have to touch anything. You know, hey Google or hey Siri, you know, what's a polygon? We had to go to the library and just do some Dewey Decimal System and look it up. And if they didn't have it in this library, go way to the library. Well, that's a small library, so oh my God, we got to go up to Steele there in Elmira library, a big one. So yeah, take advantage of that. But not because in class can't have phones later on today, right? So a polygon is just a multi-sided figure, right? So we have equilateral polygons. Yeah, so equilateral, lateral meaning the sides of it, right? So that means all sides are congruent. All, you know what congruent means? Yeah, the same, they have equal measures, okay? All sides congruent. We're going to use that term a lot in this class. And there's a difference between congruent and equals. We'll have to flesh that out a little bit. Okay? So that's equilateral. What about equiangular? Yeah, equiangular. All angles congruent. And we have a symbol for congruent. We'll start using at some point. Say this in writing. There's a nice thing about math and algebra. It's a notation language. That's a shorthand. Feel free to use it. Now, what about a regular polygon? Well, it has to have sides. So a regular polygon is one that's both equilateral and equiangular. Okay? So it's both equilateral and equiangular. And those are the ones, you know, when someone says an octagon, that's what your brain thinks of. You can look at it as kindergarten, right? It's like you think it's a stop sign. That's a regular octagon, okay? That make sense? All right. Everybody have that? Put back here. About rotation angles. We'll talk about symmetry. A lot of the stuff is crossed out, okay? So symmetries come in most often when we're talking about reflections, okay? There's different types of symmetry. The one most obvious you know about is line symmetry, okay? Or reflectional symmetry. If something gets reflected in a line, it's like you looking in a mirror, right? What's looking back at you? Yeah, the exact same version of what you, right? Everything's the same size and shape, hopefully, right? Unless it's one of those goofy mirrors, okay? So we have, if something is reflected, it is symmetrical. It has line symmetry. Here's, you can imagine that this shape was formed by reflecting in that reflection line. It's exactly the same on the other side. It has line symmetry, okay? And different shapes can have different lines of symmetry, right? More than one, or some of them don't have any, okay? So this letter A, for example, it has one possible line. There's no line of symmetry you can draw from that letter A. Does that make sense? Can't do it this way and have it be the same on both sides or an angle, okay? Now the Z, this is no lines of symmetry. Anybody disagree with that? Can you think of one that would make it symmetrical? You could? Like where? Like this? Would it be the same? So if I was to reflect this top part down, would it map onto the other part? Use that term mapping, would it? Okay, so no. Butterfly, got one line of symmetry. Anyone know what kind of triangle that is with all three sides and different lengths? Well, so obtuse refers to the angle measures. I'm talking about the sides. It might be, well, now isosceles is going to have at least two sides congruent. So what you did is you fired out a name of the triangle you heard, right? You took a shot. Okay, good. It's scalene. Heard that term? Scalene. All sides are different lengths. Well, now you've heard it. Okay. I have this little rose petal-y thing here, and it has 6 lines of symmetry. This square has 4 lines of symmetry. Would a square be a regular polygon? Is it equilateral? Is it equiangular? Aren't those the two things that make something regular? Well, a square is a regular polygon. It has 4 lines of symmetry. How about that parallelogram? Do you think we can get a line of symmetry in that parallelogram? If we draw it, would you be able to reflect it somehow to map exactly to the thing on the other side? No. Whatever that thing is there, has no lines of symmetry. Because sometimes you have to look at like the little details inside and they also map too, okay? So let's take a look at some examples here. We'll look at the first one with you. So we have this arrow here. How many lines of symmetry do you think it has? I would say just one, like right through there, just one. That next one there, number 2, how many lines of symmetry? One. Just one, right? Remember, the line of symmetry, it has to reflect over that line and map exactly what's on the other side, right? So that would have just one. What about this deadly looking thing here? Yeah, I think we can get 2 out of that. One that way vertically, another one horizontally, so 2. And this lesson brought to you by the letter B. How many lines of symmetry? I think just one, right? Right through there. So just one. All right, why don't you guys take a second then, and do the same thing we just did here with this next one, number 5, right? See line of symmetry, sketch it in there, and make it number. About half a minute. Who didn't?
Say it, but I know.
Say it. Even if it's like you don't know. Don't forget to record. Okay. So let's do this here. Note number 2. We need, and some of this is saying, but we need to know about equations of lines and whatnot, okay? So, with the graphically, certain lines look like. So if I have the line say y equals x, does anybody know what that looks like? So remember how you did like a little table of values at your kindergarten there to graph your lines, right? You had x, and then you had y, and x, and y, right? So everywhere on this table, the x and y's are the same value, right? So give me one ordered pair that would be on this line. What comma what? 5, 5, 5.
6,
0, 0. Negative 10 million, comma negative 10 million, right? Right? So 0, 0, 1, 1, 2, 2. Would it not just be this line right here? Right? The line y equals x. What about the line y equals negative x? Yeah, kind of the same, but x and y are exactly equal, right? Whatever x is, y is just the negative of it. So wouldn't that just kind of reflect that line over there like that, maybe? Okay. What about, say, the line? And this is where kids get confused, but we need to get this straight. The line x equals 2. So I would say every single ordered pair coordinate on this, x comma y, has an x value of what? 2, because it's x equals 2. So 2 comma 0, 2 comma 4, 2, 5, right? 2 negative 10,000. But the x is always what? So this line will cut through the x-axis at what value? At 2. 1, 2. And I'll do this so it doesn't look like an axis. Would it not just be that line right there? Right? A lot of people get it confused. They always want for some reason to make it the horizontal line. But that would be y. Just remember, when you see this, okay, what's the graph of that? Okay, what axis does it cut through? What's that say right there? X-axis. And where does it cut the x-axis at? It's that simple, right? So let's try the line. Yeah, y equals negative 3. Every single y value on this line has a value of what? Negative 3. So what axis does it cut through? The y-axis, and where does it cut the y-axis? Down here at negative 3. Does that make sense?
Yeah.
So we kind of keep those things straight. Okay? All right. Let's take a look at, these are Regis questions. These are actual questions on past Regis exams. So what I'll have you do is we'll just start with number 1. All of you right now take a look, read number 1 over, okay? On your own. Let's see if we can answer that. Pause and someone better remind me. Okay, number 1, who's going to answer they think is correct? And if you're wrong, don't worry about it. You know, you can be wrong in here. We'll all just, we'll tease you until you develop an eating disorder or something. And that's how you learn, okay? Yes, sir.
FET.
You mean choice 1?
Yeah.
Everybody agree with that? It is. Choice FEG. So let's see what happened here. So we had triangle ABG. So I like to just kind of highlight. Triangle ABG did something to it, right? Reflected over line BG. Got reflected over this line, so it ended up over here, didn't it? Okay? And then rotated 180 degrees about point G, so then it did this, down to here, right? And it ends up at triangle FEG. Good. And recording. Wonderful. How about number 2? If I carry the rhombus on, so it means to map onto itself. What do you guys think for number 2? Joyce, what? She says 3. Does anyone agree with her? Anyone disagree? Anyone have no earthly idea whatsoever? So the question is, figure what's a rhombus. You know what a rhombus is? Well, kind of, it's that thing, whatever. It's got 4 congruent sides, but it's not a square, right? It doesn't have 90 degrees. Which transformation? Oh, did you see this, by the way? The key word there. You got to catch those. Not carry it onto itself. Okay. So a reflection over the short. This will be the shorter diagonal. Wouldn't that carry it onto itself? It'd reflect on that, right? So a reflection over the longer diagonal. That one there. We reflected it over. That would carry it or map it onto itself. Clockwise rotation of 90 degrees. Okay. About the intersection of the dead. So that center point there. Well, what about that one? What would that carry? We rotated 90 degrees. Just 90. So this side, this long side would end up where the short side currently is, right? So that would mean it doesn't map to itself. Right? So it is choice 3. Okay. Let's move along here. That's what it can be. All right, so I'll let you guys take it. Now, number 3 is where you got to think about these lines today. So you got to know. So if you got to flip back to the notes page, kind of thing. Maybe you can sketch the line in there they're talking about. It'd be helpful. Okay. So take a record now. Well, let's take a look at these. So the first one, a reflection over the line y equals x. Remember that's this one here, right? So everywhere. Okay. So everywhere on that line, you notice it's going to miss that, isn't it? Isn't it going to miss that point, right? Because it goes like down here, okay? That won't be on it, right? Because for that to be on it, it would have to be 4 comma what? Y equals x. So if this is the line y equals x, can 4, 3 be on the line y equals x? Those 4, 3 aren't equal, right? 4, 3, 3. Yeah, right? Okay. What about the line? I bet you it's going to be the same thing for the line y equals negative x, right? It's going to miss those, is it not? I did that horribly wrong. There's a line y equals negative x. Those corners won't be on. They'd have to do vertices would have to be on it, right? What about choice 3? Rotation of 90. So it's a parallelogram, right? So not all the sides are the same, okay? Just opposite sides are trying to go. We can't do choice, so it's got to be 180-degree rotation. Are you with me? Okay. Have you looked at number 4 yet?
Yeah.
All right, I'll give everybody a second to look at number 4. Go look at it. So choice number 1, it says does not carry itself onto itself. Okay? So the line x equals 5. Well, what axis did that cut through? Which axis? X-axis where? 1, 2, 3, 4, 5. It cuts through right there. That's the line x equals 5. If you reflect it over that line, does it map back onto itself? Remember, not. It does not, right? The line y equals 2, that would be here, wouldn't it? It would map onto itself, right? Y equals x, that one, right? What about x plus y equals 4? What the heck is what? Wouldn't that, what if we subtracted x from both sides? Wouldn't it be that? Y equals mx plus b. What's the y-intercept of that equation? 1, 2, 3, 4. And what's the slope? Down 1 over 1. Would it not just be this, right? Down 1 over 1. Did I get that right? 1, 2. Oh, sorry. I hit the wrong thingy there. So it'll be 1, 2, 1, 2, 3, 4. My eyes are just kind of dancing around. Then there, then would it not be that line, right? And so it would reflect back onto this. Yeah. So, but it's not. So 1. Okay. All right. What's your first set of common core geometry questions there? And you get used to these, right? Yeah.
Well, we did that last year.
Yeah, a lot of the stuff is done. We're gonna take the stuff that you've done and take it up another notch. Okay, so the homework, excuse me, for day 1, I'll just make a note of it down here. So for day 1 homework, just do numbers 1, 2, and 5. Let's work on that right now. And for day 2,